Okay, now we will be discussing site to cloud. So the easiest way to think about site to cloud is any connection to um, any device that is not an Aviatrix device, meaning any device that is outside the Aviatrix fabric is a site to cloud connection. This could be an on-prem device. This could be a device in the cloud. This could be SD-WAN. Regardless of the device, when we want to connect Aviatrix, our data plane, our fabric to this external device, then this connection is called a site to cloud connection. Okay. And here we can see it. It could be your on-prem data center. It could be third-party appliances. It could be SD-WAN. It could be a branch. No matter which connection, where the connection is heading to, this is a site to cloud connection. So there are two options. Actually, I mean, there is three options where we on where to land our site to cloud connections. I mean, do you want to terminate the this connection on the transit, or do you want to terminate the connection on a spoke gateway, or do you want to terminate the connection on a standalone gateway? I mean, standalone gateways are not really are not very common, but you can think about it like a use case where you want to do an IPsec connection or any external connection, but you don't want to exit this VPC. So you only want a dedicated connection from this on-prem location to this VPC, and you're not interested in any resources that are not within the scope of the VPC. This could be a use case where you will use the standalone gateways. Okay. Now, apart from the standalone gateway discussion, we have two options. We have the transit gateway and the spoke gateway. The transit gateway, I mean, some of the things you need to know is, I mean, BGP is supported, by the way, on both. So now on the transit gateway, let's just put next to the transit gateway here some of its properties. So BGP is supported. NAT is basic NAT, which means you can do source NAT, destination NAT. For example, there is a functionality called map NAT that is not supported on the transit gateway. We will discuss this in upcoming slides. The advantage of terminating the tunnel on the transit gateway today is the segmentation support, which means that if you are to land a tunnel, if you remember from our network domains discussion, if you are to land a tunnel on a transit gateway, you can place that specific tunnel into a network domain. This is one of the advantages of terminating the site to cloud connection on the transit. Versus if you do it on the spoke, I mean, BGP is there on both. It supports advanced NAT, which is basically map NAT. As I said, BGP is supported as of 6.6. And obviously you can, and you're not able to do segmentation support as of today. So you're able to put the full spoke in a network domain. However, if you have, I've alluded this also on the network domain session, but if you have a connection, let's say to device 1 and a connection to device 2, let me just try to put two different devices. Sorry for the sizes. So if you have two different sorry for that, let me just try to fix that. 1 second. So if you have two different external devices that you have, and you have connection 1 you have connection 1 and let's say connection 2. You are not able to put connection 1 or tunnel 1 in a certain domain and connection 2 in another domain. The whole spoke with all its connection can be in a single domain, but you are not able, again, as of today, to separate the connection 1. You're not able to basically separate connection 1 from connection 2, which is something you are able to do on the transit. So if you were to have another site that connects with transit, you are able to separate these two together by placing them into two different VRFs or network domains. Okay. The other very common and solution is to extend the Aviatrix fabric. Instead of having to deal with third-party devices, compatibility, configurations, separate management, you can launch Aviatrix as a virtual appliance on the edge of your network, being the data center or a co-location or even a branch, as long as you have a VMware or KVM as a hypervisor, you are able to launch the Aviatrix Edge on top of that and connect to the transit. What we're showing here, it might be a bit complex, but in a nutshell, what they're doing is you have a direct connect location. A direct connect location is simply where the different clouds, example in this discussion is AWS. This is why we call it a direct connect location, where they have their, you can call them the meet me locations in Azure. Basically, it's how you can connect into the AWS network. So they have their own router, okay? And you can have a router, or your colo provider can have a router. Basically, you need to have a router in that facility, and you will connect back to back to the AWS router, which will then take you into your VPC and into your network. So what they're doing is you have already an underlay that connects this colo router into the VGW. And on top of this connection, you are running a connection as an overlay between this on-prem router and these two transit gateways. So you're leveraging the direct connect as an underlay and running as an overlay to do end-to-end encryption from this on-prem router or on-prem data center up to the transit gateways in AWS. They're leveraging the direct connect, which is the private circuit, as a primary path, and they already built another connection that is over the internet as a secondary path. So this is the, if you want to think anything over the internet is secondary, anything that is over the direct connect is the active or the primary path, okay? So this is a possible setup. Now let's look at some use cases that mainly pertain to SaaS providers or multi-tenant architectures. It will probably be more, I can explain it probably easier, the problem and what we can do. So let's assume that you are offering a shared service, right? You have a service that you want to offer to enterprise customers. And so you build what is spoke VPCs. Maybe you have some local services, so you offer services for each customer. So what we're doing here, you think about like you are a service provider that provides services to multiple tenants. This could be infrastructure, this could be applications, whatever that is. So you can create a landing VPC for these different tenants. So each tenant one will have its landing VPC, tenant two will have a landing VPC, tenant three will have a landing VPC. And then what you will need to do is you will need to connect this tenant VPC into this landing VPC. I mean, mostly by using IPsec and BGP as a routing protocol, so that these workloads or even the workloads on-prem are able to benefit from the local services. So these are services that are available for each tenant. On top of that, there are some shared services. These are services where all of the different tenants need access to a common set of services, okay? And the reason this is, I would say, the more complex and the reason we're going to discuss this is that you, as a shared service provider, you only have access up to this point. You do not have access on the red portion. You do not have access on anything on the tenant network. So this is the boundary here. This is the boundary, and this is where your control actually ends. And the reason this is important is tenants could have IP addresses that are overlapping, and there is nothing you can do about it. But you still need to provide them access to their local services, but more importantly, to the shared services that they need to access. Okay, so now let's look at the problem. You have, let's look at tenant one. Tenant one AWS account has a VPC that has a side range of 192.168.200.0/25. The problem is that tenant three, which on VPCB, is also using 192.168.200.0/25. Now, there is no problem. Generally, what you will do is when you have a multi-tenant architecture, you will create network domains or segmentation domains. So in this setup, we are creating the shared services as a domain and each of the other tenants as a network domain. And then because everybody needs access to shared services, what you're seeing, these lines are actually the connection policies, so that all of the tenants are able to reach the shared services tenant. Okay, now the problem becomes, so 192.168.200 is available twice. So whenever, let's assume that the traffic gets into the transit and into the shared services. Where is 192.168.200? We see the address twice. We see it once learned from over spoke 1 and over tenant 1, and once learned over spoke 3 and tenant 3. So this is not going to work, right? Because you have the same address that wants to access your application. This is not an issue for the local services, because the local services are in a network domain, and I mean, basically, they are not going to share the routes between tenant 1, tenant 2, and tenant 3. However, the problem is because they all want to access a common service. So how do we tackle this problem? We can tackle this problem by leveraging NAT. And this one is an example of source NAT. So what we're doing is, on spoke 1, again, we don't control anything on the tenant network. On spoke 1, we are doing a policy-based NAT, policy-based source NAT to be specific, whereby we say if the source is 192.168.200, which is the traffic that is, which is basically the tenant 1 side range, and if the destination is part of the shared services, again, this is where the problem happens, we will change the source address from anything in the 192.168.200 range to 10.0.101.10, which is the IP address of the gateway. By the way, this should be a 10 here. This is a typo. Okay, so as the traffic flows through the spoke gateway, if we see that the traffic is coming from 192.168.200, if it only wants to go to 10.0.200, we are going to change the source IP address of that packet by replacing it with the gateway's IP address. This way, when the traffic goes north towards the shared services, the source address of the packet is going to be 10.0.101.10. And the reason this solves the problem is now when the shared services gateway wants to route the packet, there is only one unique 10.0.101, and there is only one unique. We do the same thing, by the way, on the spoke 3 VPC where 10 and 3 is connected. And this way, the traffic that comes, traffic that comes from here will be 10.0.101.10, and on the other side, traffic that comes from spoke 3 is going to have 10.0.103.10. Okay, this way, the shared service gateway is easily able to distinguish where is 10.0.101 coming from, where is 10.0.103 coming from. And by doing this, we have solved the overlapping address issue by leveraging SourceNAT. In addition, the segmentation is solving the problem of accessing the local services, even though the addresses of these tenants are overlapping. Okay, so this is how you can use segmentation with NAT support. Again, this is somehow the same thing. You're seeing customer 1 on-prem environment, customer 2 cloud environment. Doesn't matter if the customer is on the on-prem or on cloud. What matters is they need to access a common service, and they have an overlapping address, which is 192.168.0.0/24. So you will basically be connecting to the on-prem router or to the cloud router via a site to cloud tunnel that will land, in this case, on the spoke gateways. And after the traffic gets here, this is where you will configure the customized SNAT as long as the traffic matches the policy. And this is how you could deal with overlapping IP scenarios and provide them also local access to services as well as access to shared services. Another very interesting functionality is MapNat. This is a function that works only on spoke gateways. The problem statement is as follows. You have an on-prem location, for example, or this could be cloud that is not under your administration, but there is basically a requirement to connect a location into the cloud, and there is an overlapping address. You can see the subnet in AWS 10.5.16.0, which is part of the 10.5/16 VPC's header range. And there is the London on-prem DC also has that overlapping address range. You do not want to touch the on-prem router. Maybe it's very old. Maybe you do not have the staff that have the proficiency to do this. You want to keep it as simple as possible without touching the on-prem router. The other very interesting requirement is you want to preserve host information, which means you do not want to add all of the IP addresses into a single IP, because this will lead to loss of visibility, because now all of you, when you're investigating an issue or a problem, everything that is coming from London on-prem DC will be changed or will be NATed to a single IP address, and you will no longer have visibility on who did what. And obviously, the simplicity of how you can achieve this is very important, because you do not want to configure 100 NAT rules, for example, for 100 hosts, and this would be very unscalable. So the solution is MapNat with route-based site to cloud. What's nice is it's very easy to configure. I'll probably explain it on the next slide. So what we do in the only 4 things you need to configure MapNat, which I think is genius, is just these 4 requirements. So there is the real and virtual. I'll explain. So first of all, you have an overlapping address problem. So your real subnets, local means from the perspective of this gateway, the cloud side, this subnet is local, and the on-prem side is remote. So anything on-prem, again, because we're looking at it from the spoke gateway side, this is the remote and this is local. So this one, I think, is very easy to understand. Then there is the real versus the virtual. So the real is the overlapping, is the actual address that has the problem. So the real address is 10.5.16.0. So you can say local real or local subnet real is, again, local means the cloud, and real means the overlapping address. So it's 10.5.16.0. Now, the remote real is also the easiest to understand, because now we're looking at the on-prem side, also the overlapping or the challenging. The real address is 10.5.16.0. You can think about real as the address before any NATing comes into the picture. Okay, so the local real and the remote real are overlapping, as we have expected, as we have defined in the problem statement. Now we will create 2 new subnets. One subnet that maps to the local side, represents the local side. So the 172.5.16.0 represents the local 10.5.16.0, and the remote virtual, again, this is called a virtual, local virtual. Okay, local subnet virtual. Again, local because it's in the cloud, virtual because we are adding it into the picture. We can add 2 subnets that do not exist anywhere in your network, preferably. And in order to maintain host information, the size of the virtual subnet has to be the same as the size of the real subnet, in order to avoid any pathing or NAT overload. Okay, so we decided here to use 172.5.16.0. Again, this is called local virtual. Now, the same thing we will do for the on-prem side, but this time it will be the remote subnet virtual. Okay, again, virtual because it is going, the 192.5.16 is a representation of the 10.5.16 that is on-prem. So this is how we've explained it. Again, the remote real, I'll just try to help you understand the 4 again. Since we've said real and we said remote, remote is the side that is not, that is farthest, that is not local, basically, to the spoke gateway, which is going to be the on-prem side, and real is the problematic. So this is how we figure out it's 10.5.16. Now, the remote subnet virtual, again, we are remote, but this time we are looking for the virtual subnet that has to be of the same size that will represent this remote real, which is the 192.5.16.0, and then the local real And because now we're looking from the spoke gateway, the local real is 10.5.16.0, again, without doing any NAT. And the local virtual is the subnet we have used to represent the local real, which is going to be 172.5.16.0. It goes without saying that the virtual subnets that we have created have to be unique subnets, and they have, as I said, they need to have the same size as the size of the real subnets in order to avoid any pathing or NAT overloads. Okay, so I think it will become clearer when we look at the packet walk. So now we have a packet that goes from the source 10.5.25.71, okay? But notice one thing, it does not actually go to 10.5.20.239. So this is the source. Again, let me just make sure we are on the same page. So the source is this host, and the destination is this on-prem server. However, when you look at the packet, the source IP is correct. This is the source. However, the destination is not 10.5.20.39. The reason is if we put the same destination, that packet will not even leave the VPC router. The VPC router sees this subnet as local, which means it will never send the packet even to the spoke gateway. So in order to solve the problem, we leverage this remote virtual in order so that we are not sending the packet to 10.5, we are sending it to 192.5. Then we talked about preserving the host information. So I'm not going to do the full subnetting, but if you look at the 10.5.20.239 and you do the /20, you will realize that 20.239 is the host portion and 10.5 is the network portion. So now when we create this destination IP, it's going to be 192.5 because this is the subnet that represents this remote local, which is the 192.5, which is the remote virtual representing the remote local of 10.5. And we are going to preserve the host information. So 20.239 is the host information, and this is why you see 20.239 in the packet. And if obviously you might not want to remember all of this, so you can configure the DNS to point to these virtual IPs instead of pointing to the real IP of 10.5.20.239. Okay, so as I said, we cannot send the packet to 10.5 because the packet will not leave the VPC router. Thus, we send it to the remote subnet virtual, which is 192.5. We preserve the host information. So 20.239 is the host information if you do the subnetting. Thus, you can see it in green. The 192.5, which is the reddish, is the network portion. And we take the 20.239 from the host information. Again, the 192.5 is coming from the remote virtual that represents the remote real for the London on-prem DC site. Okay, so let's see what happens to the packet. Once the packet goes through the spoke gateway, the spoke gateway is going to do a source NAT and a destination NAT. So again, we're not going to touch anything on the CSR. So we have to change the destination IP, because if we do not change the destination IP, that server will never reply. If you cannot go to 192.5 and expect the destination to reply. We need to change the destination IP to be the real IP of the server. However, we cannot go, again, the same problem with 10.5, because if we go with 10.5.25.71, the packet will not even leave the site because it is part of the on-prem DC side range. So we will change the source IP to from the real IP, which is 10.5.25.71, to an IP within the range of 172.5. And again, we preserve the host information 25.71. So we have done both a source NAT, whereby we changed the source IP from the real IP to an IP that comes from the local virtual range of 172.5 while preserving the host information, the 25.71. And we changed this virtual fictitious IP 192.5 that we have created into the real IP so that the server will actually accept the packet and respond. Okay, it might be a bit cumbersome, but it's basically doing source NAT and destination NAT and preserving the host information, all by filling these four pieces of information. So the packet goes through the CSR. Again, CSR, you don't want to implement any change. And when you do a TCP dump on the host 10.5.20.239, you do not see, obviously, the packet coming from 10.5. You will see the packet coming from the 172.5.25.71. Okay, so now when you want to respond, you will have to respond to the 172.5. This is what we will see in a second. So now you see the packet coming from 10.5.20.239, going to the 172.5.25.71. Again, this is the IP. You cannot send a packet from 10.5.20 to 10.5.25. This packet will never make it through. So we are sending the packet to the virtual IP that represents this host, which is 172.5, and preserve the host information, which is 25.71. Again, no change on the on-prem router. I think now you'll expect what will happen. We'll do always source NAT and destination NAT. So the 10.5 has to be changed by the spoke gateway to the 192.5, which is again the IP address that represents the this remote server on-prem, always preserving the 20.239. And we need to change the IP because this server will never respond to 172.5. So we will change it to the real IP address of the server. Okay, again, this is the beauty of MapNat, doing all of this at scale while preserving the host information and without having to touch your on-prem router in a very simplified manner. Again, worth noting that MapNat exists only on spoke gateways today. It does not exist on the transit. And again, if you do a TCP dump on the 10.5.25.71, you will see the packet coming from the 192.5 IP address as expected. There are more use cases for overlapping addresses in our documentation that you can look at. Another interesting feature is BGP route approval. And I think it's really important. And if you've seen somehow lately in the news, there are many outages for major corporations that were due to some BGP advertisements. So what we're doing here, the problem is generally in BGP, it's hard to control incoming updates. I mean, you can always put some route maps and approvers, but generally, the way Aviatrix does it is very interesting. Aviatrix BGP route approval, it will require the admin's explicit approval to insert and propagate a route. What I mean by this, if you have a partner and the partner sends routes via BGP, if you don't have BGP route approval, the route will exist now in the transit, and this route will be propagated to all of the spokes and to the whole fabric. With BGP route approval, what will happen is, again, I mean, one of the use cases is obviously to prevent bad advertisements, wrong advertisements, default routes, overlapping advertisements, things that will cause problems in your network. So when you get this advertisement, you do not propagate anything, and you do not insert it into your forwarding plane. The transit gateway will send this to the controller, and the controller will send an email to the administrators stating that there is a new route that we have received from this connection. Do you want to approve this route? So only when the admin approves the route, this is where the route will be programmed into the control plane, and then it will be propagated to the fabric, to the spoke gateways. Okay, so before approval, even the transit itself will not consider the route, and the spokes will not even have the route. Post approval, this is where the route spreading will actually happen. What's interesting is you can enable it on the full gateway or on a specific connection. The reason this might be interesting, maybe you have 5 connections to this transit gateway, but you do not trust one of your connections. Maybe you know that the administrator there is new or might not be very skilled with BGP, so you're worried about, or you know they're making changes and you don't want any of these changes to affect you. So instead of accepting all of these routes, you can say, hey, for this connection, this is where I want to do BGP route approval. So you can be, maybe for only this connection, I want to enable route approval, and for the others, I can keep it off. Okay, so you can be very granular on where to enable BGP route approval. Aviatrix Edge. So Aviatrix Edge is, again, all about extending the data plane, extending the operational advantages, extending things like high performance encryption to the edge in a very simple manner without having to worry about operations, about upgrades, about troubleshooting. You will use the same operational model, the same alerting, the same visibility, the same flow IQ, everything that we have been discussing, and just extend that advantage onto the edge of the network. And one of the very common use cases is to have high performance encryption. If you remember, high performance encryption works between any 2 Aviatrix gateways as long as both of these gateways have HP enabled. So if you have an on-prem data center where you're running maybe VMware or KVM, and you can run the Aviatrix Edge on-prem and have a high-performance encryption connectivity from your on-prem data center to the transit on top of things like your direct connects or express route or any private connection, which enables you to do to get the benefit of the throughput as well as encryption without having to compromise any of them. Okay. This is one of the use cases that has become very prevalent. And one thing to mention is you can also bring up Edge in the Equinix marketplace. This is, again, a great use case for the same pattern where you can run high performance encryption from Equinix into the cloud service providers and then back into your data center. The other one is multi-cloud connectivity. This one is really another very interesting scenario where you have 2 different CSPs. This could be AWS, Azure, GCP, OCI, but we're just giving the example of AWS and Azure. And you would like the traffic between these two environments, I'm talking about AWS and Azure, to go through on-prem. Why? Because you have already procured some private circuits. I'm talking about things like Direct Connect or Express Route. And these links are very low latency, high performance links. So instead of the traffic between AWS and Azure to go over the internet, you would like the traffic to actually go over the through the on-prem location to the other cloud. Okay, again, because of this is high performance, this is low latency versus the internet. Okay, this is very, again, what you could do is you can also benefit from edge being here, because edge being here also means that you have high performance encryption. So your traffic between AWS and Azure also is being encrypted at high throughput, again, with all the simplicity that edge brings into the picture. And what you could do is you can manipulate routing in a sense to make the internet link between the two transits a backup link, and via ES path prepending, and to prefer the path that is via the edge. This way, the traffic between the two CSPs will actually flow through the on-prem location or data center. And if any of the links were to fail, you have the option you will fail back automatically to the internet link until that link fixes itself, and then you will go back to leveraging the private circuits. Okay, so we're leveraging the private circuits not only to connect on-prem to the clouds, we're also making this location as a transit point or as a hub to connect the different cloud service providers. And if any failure were to happen, we are able to fail back to the internet. So a bit on the edge deployment workflow. The way it works, because now you are deploying a virtual machine, right, in VMware. So how are we going to give that virtual machine its configuration to find the controller, sort of a zero-touch provisioning or bootstrapping? So you will go to the controller and create this zero-touch provisioning file. Next, you will deploy the virtual machine, just like any other virtual machine on VMware or KVM. Once you deploy the virtual machine, you will need to provide that bootstrap file, that zero-touch provisioning file, to the virtual machine so that the virtual machine can go and register itself to the controller. Okay, so this is, you create that file on the controller, you download the file, you spin up the VM, you attach the file to it, and then it will register to the controller. And once this is done, you can, your control plane is completely done, and everything about this edge can be configured from the controller. You can finally, from a data plane perspective, you are able to attach the edge to the transit. And obviously, you might have some sort of form of a LAN routing device, and you can run BGP over LAN to share routes between the cloud and on-prem via the edge. And this is just a bit on how you can deploy edge. Again, the benefits are leveraging the same operational model, high performance encryption, and simplicity. You don't have to configure IPsec. You don't have to worry about interoperability. This is treated like another spoke gateway. So again, when you connect to external devices, here I want to touch upon two things. The fact that what encapsulation you want to use. And when I talk about encapsulation, generally I'm talking about three different possibilities. One of them is to do IPsec, which is very commonly used specifically because it provides encryption. And many times we want to ensure that our traffic is end-to-end encrypted. Now, the downside of general IPsec is that it provides approximately 1.25 gigs per tunnel. And we discussed how Aviatrix solved this problem with high-performance encryption, but this is IPsec generally. The other possibility is to do GRE. GRE does not provide encryption. However, from a performance standpoint, it provides around 5 gigs per tunnel, which is approximately 3 to 4 times what IPsec provides. Again, if you are only okay with no encryption, the other downside of GRE is that, for example, it is not available in all CSPs. Okay, I believe Azure does not support GRE. Now, the third possibility is not to do encapsulation. Meaning, if I have like an SD1 headend that is already in the same VPC as the transit, I can put it even in the same subnet, and they could be like connected back to back. Thus, I do not need to build a tunnel to reach the device that lives back to me. So think about, when we talk about no encapsulation, think about like old school networking where you started to learn routing, and you can have 2 routers and they're connected via a cable, and you want to run like a routing protocol on top. Even, by the way, I'll extend this just so that we're 100% clear. Even if you were to have 10 routers in the middle, okay, if you have connectivity, if you have like, you're running a routing protocol and you have connectivity from, let me try to distinguish this. If you have connectivity from the router here, I want to do it in blue. So if you have a connectivity between this router and this router, okay, via OSPF, via whatever underlay routing protocol, you're able to run BGP between these 2 routers, and you don't need any tunneling because you have a connection between the interfaces or between loopbacks, wherever you're running BGP on, without the need for any overlay or any encapsulation. Whenever you hear the word encapsulation, another word could be overlay, another word could be tunneling. And whenever you're doing no encapsulation, it means you are doing it directly in the underlay. You are not building any overlays or any tunnels. Okay. Now, on top of all of these encaps, you generally need a routing protocol, and the routing protocol is needed to share or exchange routes. So the most common routing protocol in the cloud is BGP. So in a nutshell, what you could have is BGP running over IPsec, because as I said, the first encapsulation could be IPsec. And then it could be BGP over GRE if you're running GRE as an encapsulation. Or it could be BGP over LAN, which basically means BGP without encapsulation, which is just like the example that I have alluded to above with the 4 routers that have an underlay connectivity, or 2 back-to-back routers where you don't need any encapsulation between them. Okay, so I want to make sure I stress upon the different possibilities and the different choices of encaps. So IPsec is generally the most common, specifically because when you're connecting different sites, because you might want to have encryption between them. If you are okay with no encryption and you want a bit additional, but you still want to tunnel and you want a bit improved performance, then GRE would be a possibility. And the best performance, obviously without encapsulation, also will, which is no encapsulation. Obviously, no encapsulation also means no encryption in our discussion. And these are the 3 different types of encapsulation. In terms of a routing protocol, it will always be BGP, and BGP can ride on top of these IPsec connections or GRE connections, or even on top of the underlay itself without any encapsulation. So I'll show you this probably on the controller. Just give me. So if I were to go to the controller, sorry for, I'm still annotating. So if I were to go to the controller, and I will go multi-cloud transit, I go external connections. Let's say I want to connect to an external device. These are the same choices that we have been discussing. The three options below are the, sorry if I could probably use a better way. These three options are the encapsulations and the two options on top So I'm just trying to unify the colors so that it becomes easier. So these are the encapsulations. And then I'll use red. And these are the routing protocols or routing options, basically, which are basically static, which means we're not running a routing protocol or BGP. Okay, so this is what I've just showed. And now coming to SD-WAN integration. So this is all about if you have already invested in an SD-WAN solution and you're asking how can I integrate Aviatrix with it. I think it will be very clear once I get to the once I get the diagram. So again, you have multiple choices. Remember discussions on BGP. You can run BGP and you can run IPsec and you can run GRE. You can run without encapsulation. Generally, the way you would deploy, you would integrate, let's say in AWS with an SD-WAN solution, which could be a Viptela, which could be a VeloCloud, which could be any of your preferred SD-WAN solutions. You will have the SD-WAN appliances. Again, these are two availability zones within a VPC. Okay, so you have a VPC, and you will place, as always, we place one transit gateway in each AZ, so for high availability, and we'll place one SD-WAN appliance within the same AZ as the transit gateway, also from the high availability aspect. And what we'll do is this SD-WAN appliance will have two interfaces. One interface, you can think about it like the WAN interface. This is how the branches, if there are branches, you can have like multiple branches, and all of these branches will come via this interface. All of this will be orchestrated by the software-defined controller. The tunnels between the branches and the head end. Okay, so they will come via the WAN interface. And then what we do specifically for the integration is we place, you have another interface, which is the LAN interface. And notice both of one leg of the transit gateway resides in this LAN BGP subnet, and one leg of the SD-WAN appliance. So this is this interface is the interface over which the two appliances, meaning the SD-WAN and Aviatrix, they can exchange the routing information. The reason this is running BGP over LAN. The reason this probably might be a solution is generally you are in the same VPC, so you might not want to have any encryption. There is no need to do any encapsulation because, again, it affects performance. So the most optimum option would be to place them in the same subnet and just run eBGP between the transit gateway on one hand and the SD-WAN appliance on another hand. Again, you will do this obviously in both for both availability zones. So the traffic will come. So you're exchanging the routes. The transit gateway is telling the SD-WAN about all of the prefixes and CIDRs that are in the cloud. The SD-WAN is telling the transit gateway about all of the prefixes that are there in the branches. And so when traffic comes, the traffic will hit the WAN appliance, the SD-WAN appliance on its gigabit 1 interface, the WAN interface, and then the traffic will go from gigabit 2 on the SD-WAN to Ethernet 4 on the transit gateway, and then transit gateway can send the traffic to spokes or to the firewall or wherever it needs to go. Okay, so again, we've used BGP over LAN because it has the highest performance. And if you run IPsec, you are basically also affecting the performance. You're getting a lower performance with, especially, be it on the Aviatrix side or be it on the SD-WAN appliance side. Plus, if you're in a single VPC, you might really not need encryption. So the most optimum option would be using BGP over LAN. This is how it's done in Azure, and you can think about it, it's exactly the same thing. The only difference in that in Azure, we do not put the SD-WAN appliance and the Aviatrix transit in the same VNet. However, what we do is we place them in two different VNets. Again, the SD-WAN appliance has a WAN interface and a LAN interface. And that LAN interface, now in order to get connectivity, you configure a VNet peering between the SD-WAN VNet and the transit VNet. This way, you have an underlay connectivity between the Aviatrix transit gateway and the SD-WAN appliance, and this is where you can run BGP between them. So it's exactly the same thing, whereby the only difference is that the appliances are not in the same VNet. You're just distributing them into different VNets, but you're leveraging VNet peering to get the underlay connectivity, and you can then run BGP over LAN between the two appliances, and everything else remains the same. Okay, next we will go to the site to cloud lab. Okay, so team, now we are doing lab number 8, which is about site to cloud. And if you look at the diagram, we're doing a very simple use case where we have now a partner site that needs connectivity to the GCP environment. However, the partner site you can look at the CIDR ranges of both, and you can directly see, my apologies, you can directly see that there are overlapping ranges between the GCP US Central 1 Spoke 1 and the partner site, which are both 172.16.1.0. And because we are on a spoke gateway, we can directly leverage MapNet to solve this. So what we're doing is a route-based IPsec tunnel between the spoke and the partner side, in addition to MapNat, in order to solve the overlapping address problem. Okay, so this is what we are going to do. Now let's go through the steps. So the first one, this is one of the functionalities that has not been fully migrated to the Copilot. So we'll go to the controller and we'll go to site to cloud setup. So this is site to cloud and this is setup. I create a new connection and the VPC should be the GCP spoke one. Again, this is where our spoke gateway lives. So this is the VPC. The connection type should be map because we're doing MapNat. The connection name, I will copy it from the lab guide. The remote gateway type could be left generic. The tunnel type is route-based, which is the default. And the primary cloud gateway is the GCP spoke one. Let me just check. Yeah, everything is there. So the primary cloud gateway is GCP. The remote gateway IP address, again, this will be a CSR on-prem. And if you're doing the lab, you'll have access to the lab guide, but I'll get it for the purposes of being able to follow up with me. So 1 second. Okay, so the IP address of the CSR I've just pasted. Again, if you're doing the labs, you will have that in your pod. The pre-shared key, I think we could choose anything. Let me just verify. Yeah, so set a string and remember it. So I'll use Aviatrix 123. And the local tunnel IP, I can leave it empty as the controller can generate one for me. Now, what's important is these 4 fields, which are the remote real, remote virtual, local real, and local virtual. So as I said, the real subnets are the problematic ones, the one where there is overlap. So you can notice that I can take the 172.16.1 and say it is the real, remote real, as well as local real, because these are the overlapping. Now, in terms of the 2 new subnets that we'll be using 192.168.100 to represent the remote site. This is the remote virtual. So let me make sure I'm doing, so this is the remote virtual. Again, make sure again, 192.168.100 is the remote virtual. 192.168.100 is the remote virtual, and 192.168.200 is the local virtual. So the local virtual is .200. So by just filling these 4 fields, I have configured the MapNat in addition to the site to cloud connectivity with the pre-shared key. This is again the IP address of the CSR. This is the GCP spoke where the tunnel is to be terminated. It's a route-based tunnel. I gave the connection the name, and I will now create it. Okay, so after waiting a minute or so, you can see that the site to cloud connection is configured. However, its state is down. This is due to the fact that we did not configure the other side, which is the CSR router that is on-prem. Okay, so what's nice about, and this is what is stated here, this will stay down until the other end is configured, which is the CSR router. So the nice thing is that part of the site to cloud, we also provide a template, a configuration template that will make it easier for you to configure the remote side of the connection, which is the CSR in this example. So if we go to the site to cloud connection, click on edit. And if we go towards the a bit below, you'll see that you can change the configuration of the vendor, and we will choose ISR, and we will download the configuration. So if you open this text file, this is actually, let me just try to drag it here. This is a configuration template that is generated by Aviatrix. And what's nice about it is it tells you what are the things that you need to replace. Okay, so it says, please reference the Cisco documentation for your device and replace NA with the expected configuration. And what if you see, it will be very easy. For example, if you go to crypto interface tunnel, you will see that tunnel interface is not configured, tunnel source is not configured. So these are the things that we will need to fix together. Just give me a second. So, but before we go there, before we go there, we need to do a change. Let me just check it. Yeah, it wants us to go into this local identifier. Again, this has to do with how IKE works, remote identifier, and change it from the public IP to the private IP. So I already have the terminal to the on-prem device. This is the CSR. Sorry, I probably, one second, let me check if it's still there or not. Yeah. I don't know why it's being, okay, let me just make it a bit smaller. So this is the on-prem device, and let me expand it, and I want to get its private IP. Again, this has to do with IKE, the IKE implementation, specifically IKE v1. So you need to replace, exactly just like what I thought, the IKE ID of the CSR router has to be its private IP because it has no knowledge of the public IP address. So I will click on change configuration so that the IPsec negotiation can happen successfully. And now back to the terminal, it says we have to change 4 things, right? There is the crypto ISACAM policy. This is the first change. We have to, this is a template, so you might have other policies. Thus, we make sure not to provide the number, because if you have a policy 1 and we have policy 1, then you will have a problem with the configuration. So we ask the user to generally make those changes, but it makes the job much easier. So crypto ISACAM policy, I'll just put 1. I could put any value as long as you reference it. And then the second change should be the tunnel should be a tunnel interface 1. I don't have any tunnel on my device. I'll show you now. The tunnel source will be, again, if you look at show IP, there's a brief. I don't have a tunnel. The tunnel source should be gigabit 1. So I will do a GI1. And the route, there's a route that points to the local read, the local virtual, my apologies, the 192.168.200. This one should point towards the tunnel. So if I go there, I should find the route. And again, because we have configured tunnel 1, this should be tunnel 1. This is everything about the configuration. You could cut it, but I will basically even take it all because the other stuff will be taken as comments. I'll do conf t and I will paste. Obviously, the last stuff will basically be rejected. But now I can do a show IP interface brief. I can directly see, this is very interesting, that the tunnel is actually up. So again, you can see how much Aviatrix simplifies the process. We have provided you the template you just had as a user to make very few changes to the template in order to get it to work with your existing configuration so that we don't cause any configuration conflicts. And you can see directly that the tunnel shows as up. If you give it a minute, it will take a minute or so. Then we will be able to see that the connection is also up from the Aviatrix side. Okay, so having waited for a minute, now you can see that the tunnel is actually up. Even what's nice, if you go to the topology and refresh it, you will see, if you click on the GCP spoke, that not only you can see the test instance in the spoke, but you can also see the tunnel connection that we have configured towards the external side. If you are to go also, another nice view of things could be, if you go to cloud routes, you can see, by the way, this will update in a second or so, but you are able to see the status of the site to cloud tunnel. What is the tunneling protocol? What is the IP address? What is the peer IP, which is the CSR's IP? You are able also to see, we're not running BGP, but if we were running BGP, you would be able to see the BGP routes that are being sent and received to that partner. Okay, so now that we have verified that we are going to ping the GCP US Central 1 Spoke 1 Test 1. Okay, so let's see how are we going to ping this instance, because remember that the IP address of the instance is, let's check it, it's in the 172.16.1. So if we look at again back at the topology, and this is the GCP US Central 1 Spoke 1 Test 1, you will see that the instance has an IP of 172.16.1.100. And if you recall, when we configured it was a /24. So whenever we configured the site to cloud, just a second, sorry, I got, yeah, so we're gonna go to the on-prem partner. So we are pinging from on-prem to the cloud. So we are going to look at the local virtual IP, which is local virtual, which is 192.168.200. And if you recall, the last octet of the test machine is 100. So as a result, we are going to ping 192.168.200.100. So let me try that. So ping 192.168.200.100, sorry. I should have specified the source. Otherwise, the ping would go. Yeah, and I can make it repeat. Yeah, so this is basically proves that the ping actually went, as I said, to the virtual address, and all of the MapNet stuff will actually happen automatically for you. Okay, you can even go, what we're showing here is if you go to that spoke gateway, and you go to gateway diagnostics, and you go to active sessions, and you run. You should be able to see, yeah, you should be able to see the ping coming. I believe the original source IP is 1.192. So I can, by the way, search it from here, 172.16.1.192. It is going to the 200.100, which is the virtual address. Again, the reply will come from the original IP to the SPO gateway, and the destination IP is not going to be the same. It's going to be the mapped IP to the 172.16.1.92. That's why you see the 192.168.100.192. So this is a very quick proof to show that the both source NAT and destination NAT map NAT is actually working as we have explained. And this marks the end of lab number 8.